For part 2 of the Chapter 1 lecture, we're going to be talking about significant figures, calculation with measured numbers, accuracy, and precision. When we talk about significant figures, we are talking about a measure of accuracy in measurement. I think we can all clearly see that between these two rulers, one of them is going to give a much more accurate measurement of the flash disk, as far as how wide it is. Now, we can clearly see that the ruler with the more markings will give us more precise measurements. If we just need a quick estimation, the top ruler is fine, but if we need a more exact measurement, we would need the bottom ruler. When we do these significant figures and have them, it's based on actual measurements, whether that's a length, a mass, a distance, etc. So when we're trying to figure out significant figures, this is often the hardest part for students to truly kind of get a grasp on and wrap their heads around. Which numbers are significant and which ones aren't? Well, the first and easy answer is any number 1 through 9 is significant. Any number that's not a 0 is significant. That's the easy part. The hard part is figuring out what happens, which are significant, when you do have zeros. Okay, so any 0 that is located between any numbers are significant. So the 0 between the 3 and the 5, that is a significant 0. I refer to those as captive zeros. They are captive between two significant figures, and it doesn't matter if a decimal is present or not. As long as there is a digit to the left and to the right, no matter how many zeros are in between, those zeros are significant. In fact, I could say this. Okay, I could say that number right there, 200,000.00, that's supposed to be a 3. Sorry about that. All of those zeros are counted. So this number would have 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits. When we talk about zeros to the left of the first non-zero digit, they are not significant. I call those leading zeros. We're going to have leading and trailing zeros. So the leading zeros here are simply placeholders. They are placeholders to give the 2 and the 3 a value. For example, if you were supposed to get a paycheck for $340 and you only got a paycheck for $34, you might say, well, Mrs. Meriwether, that 0 definitely is significant. And I would say you are wrong. It is necessary. That 0 is necessary, but it is simply a placeholder. It's important. We need it there because clearly $34 is not the same as $340. But by having that 0 there, it is simply just necessary. It gives the 4 a values in the tens values. It gives the 3 a value in the hundreds value. That's why we need it. But it is not a significant digit. Much in the same way, these zeros are simply placeholders. They are just there to give the 2 and the 3 their values of 1,000s and 10,000s. Okay? Zeros to the right of the last non-zero are significant if and only if there is a decimal point. So these zeros here are significant. They are trailing zeros. Trailing zeros are significant if there's a decimal. If there's no decimal, then these are no longer significant. If I had 1, 2, 0, 0 decimal, they now become significant. The reason for this is those zeros came from something. Perhaps the original 1.200 was, oh, let's say it was originally 1.9, not 9, hold on, let me erase that. Let's just pretend that was originally 1.987. Well, if we had to round, then we would say, if we had to round at this place here, we would say, okay, that 9, oh, and that 8, they are over 5. Oh, and so is this 7. So perhaps it rounded to this number right here. Okay? Those zeros came from somewhere. Then there are zeros that to the right of the last non-zero in any number that doesn't contain a decimal point is not significant. I just did an example of that. So 1, 2, 0, 0, not significant. So this number only has 2 sig figs. But 1, 2, 0, 0.00 now actually has 1, 2, 3, 4, 5, 6 sig figs. Okay, all those zeros count simply because there's a decimal. When we're talking about significant figures in terms of scientific notation, what we mean to say is that we will write any long number in a shorthand way to bring it to a power. So we can, it's basically just a shorthand way of writing a really big long number. So if I am going to maintain significant figures, the generic format for this is, I always do 1.23, I don't know why my decimal's not writing right now, 1.23 times 10 to the n power. Again, don't know why this decimal keeps disappearing. There we go. These will be however many significant digits are in the original long number, and n is the power to which the multiplier, how big the number is. You remember, positive powers means the number is greater than 1. Negative powers means the number is a decimal. So for example here, if I were to write this in scientific notation, first I would have to figure out how many significant digits there are in each thing. I can already see there's a typo. I believe this number 3 is supposed to be a times sign. So this should be 3.000 times 10 to the minus 7. Okay, I believe that's what it's supposed to be. It just looks like a typo. So letter A has 3 significant figures, and I could write it in scientific notation as 4.43 times 10 to the 2. 15.03 has 1, 2, 3, 4 sig figs. That 0 is counted because remember it's considered a captive 0. So I could rewrite this in scientific notation as 1.503 3 times 10 to the 1. Okay, notice I only moved the decimal 1 spot, so that's only to the power of 1. And I wrote all the significant figures that are there, and I also maintained the singular number, decimal, and the rest of the sig figs that are present. Okay, for letter C, these zeros are not counted because they are leading zeros. So it has 1, 2, 3 significant figures. I could rewrite this as 3.56 times 10 to the minus 2. Negative power means it's a decimal, and I've just simply moved my decimal 2 spots. Go ahead and figure out the rest. You can pause this here. Letter E, we would not write in scientific notation. My rule of thumb is any number that has 4 digits or less regardless of decimals, we just leave as is. Anything that has more than 4 digits, go ahead and put into scientific notation. So letter E, we can say has 1 sig fig, and that's the 5. The 0 is not counted because it is a trailing 0 and there is no decimal present. Letter F has 1, 2, 3, 4 sig figs. This is not counted because it's a leading 0 and there's no other number to the left of it. When we add, subtract, and multiply and divide, we are limited differently by how many significant digits our final answer should have. Adding and subtracting, we look to the right of the decimal to see which number we added or subtracted limits our answer. So when we're adding, subtracting, we're looking after the decimal. The number with the least amount of significant digits after the decimal is the number that will limit our final answer. So we still add them just like we would add any other numbers, putting it into your calculator. But then, if this is our final answer here, we actually have to round it so that there's only 2 significant digits after the decimal, because this number here, the 102.50, limited us because it only has 2 significant digits after the decimal. Subtraction, the same rules apply. Subtract just like you would normally subtract any other numbers. If this is your number you get, your final answer can only have 1 digit after the decimal, 1 significant digit after the decimal, because the 20.1 limited us. Okay. All right, multiplying and dividing, we are no longer limited to just the numbers at the end of the decimal or after the decimal. We look at all the numbers involved and find the one that has the least amount of significant digits overall. So here, 1.4, that has 2 significant digits. 8.011, how many significant digits do you think it has? Basically, does that 0 count or not? The answer is yes, it does, because it's a captive 0. So 8.011 has 4 sig figs. Multiply just like we'd multiply any other numbers. This is our final answer. However, the 1.4 limits us, so our final answer can only have 2 significant digits. Okay? When we divide, we do the exact same thing. The 305.88 has 1, 2, 3, 4, 5 significant digits. The 11.57 has 4, 1, 2, 3, 4. So our final answer can only have 1, 2, 3, 4 significant digits. So we would have to round our final answer to be 4 significant digits. Exact numbers are considered to have an infinite number of significant figures, and they do not limit the number, okay? We just have an exact quantity. So for example here, 3 times 2.5 grams is 7.5. This is an exact number. When we talk about rounding errors, we talk about this in terms of rounding errors when there's multiple steps involved. Perhaps first you have to add some things together, then maybe the next step would be to multiply, then divide. We're going to have lots of mathematical computations like this. The best rule of thumb is to never, ever, ever round until it's your final answer. And then you need to look at what your parameters were to decide how many significant figures should be in your final answer. You do need to understand this. When we get further into the semester and we start doing stoichiometry and multiple calculations and all these different things that you've never been exposed to before, you only choose what's going to limit your significant figures in your answer based on given information. So it's given information only. Okay. This is because you're going to find that there are many conversion factors that are for example, 1 gram equals 3 milliliters or something. So you'll have a lot of conversion factors where it'll be 1 of something equals something. And that 1, therefore, would then always limit you. But really what it is it's just a way to convert from one thing to another. So we only look at given information when we get into the more complicated problems that are dealing with the chemistry of it. And I'll remind you of that as we go further. I want you to take a minute and perform these operations and see if you can get the final answer for how many significant digits you should have in your final answer. So just to start off, for letter A, your final answer should only have 1 digit after the decimal in your final answer, because the 317.5 limited you because it only has 1 significant digit after the decimal. Okay? Here's the solution. You can go through that, but I want you to practice those problems. Now when we talk about accuracy and precision, we use those terms a lot, but very loosely. In chemistry, it's those are 2 very different terms, even though they sound very similar. You know, how many times have you said, gosh, that was a pretty accurate throw, or I want to be really precise with my handwriting and drawing. Well, accuracy tells us how close to the end goal we got. Did we hit the nail on the head, so to speak? Did we get the bullseye of the target? How close did we get a true value? Okay. Precision is how many times can we repeat that? So I go out and shoot a bow and I hit the bullseye of the target once. That was very, very accurate. How precise I can be tells me how many times in a row I can hit the bullseye. So here's just an example. We have student A, student B, and student C. Which one was the most accurate? Well, let's just say our number to be accurate was 0. They're trying to get a measurement of 0.334. Let's just pretend, okay? So the one that was most accurate was student A, okay? B, well, gosh, these measurements here are way off. Not only are they not close to 0.334, but they wildly range. So even if he's getting the wrong measurement, or she is getting the wrong measurement, they're not even repeating the wrong measurement more than once. Student C, completely the wrong measurement, but is pretty accurate in repeating herself. Not as accurate as student A, but still not too bad. So for overall accuracy and precision, student A is getting it the most close to our desired amount, and they've been able to repeat it pretty well. Here's just another example of student A, B, and C. So, oh, here, they do give you the answer in this particular one. In this particular chart, they're telling you that the accuracy and precision was meant to aim at this right here. So now our answer of who did it best is changed. So you can see that A, pretty precise, pretty hit the nail on the head closely every time. Student C, still pretty accurate also. Student B, he's all over the place. It's terrible. He's going to get fired from his job. But C, student C, not only hit the nail on the head and hit the bullseye pretty accurately pretty accurately, but they also were able to repeat it multiple times. So now student C is our winner for both accuracy and precision. I don't know why my writing keeps disappearing. I'm sorry, I'm trying to reference things here. So remember, we wrote 4 quarters for every $1 bill. So if I had $5.63, I'm going to put the dollar bill part at the end because remember, units come at the end. And I wanted to convert that to quarters. I'm going to say I want to get rid of dollar bills and I want quarters, so it goes in the only spot I have left. Now my bills have canceled out. And now and only now do I put in my numbers. My 4 stays with its buddy unit, the Q. My 1 stays with its buddy unit, the dollar bill. When I take 5 seconds and do it this way, I never get it wrong. I always put everything I need in the correct space so it cancels out. Now what I'm going to do is I'm going to go ahead and multiply the top across, and I'm going to do that with my calculator. So let me just do that. 5.63 times 4. So that's 222.52 quarters over 1. And of course it's over 1, so I don't really need to divide that, but I know that it would be 22.52 quarters in $5.63. Here's another example. If you wanted to take it more than one step, let's say you had inches and you needed meters, then we can have 2 conversion factors. Here we have inches, and I put my inches to where it can cancel out. That left me with centimeters, but centimeters was not my end goal. Meters were. So I have to do one more step and say my relationship between centimeters and meters is 1 meter for every 100 centimeters. So now that I've done that, I've put the centimeters where it needs to cancel. Now those cancel, and what I'm left with is my desired unit of meters. So in this case, we followed what we should always follow for the strategies of this. Always do the given times your unit factor or factors can be more than one. Clearly, this is the first unit factor, second unit factor, will equal our unknown. If you always follow this basic format, you'll never get it wrong. Then you just let your units that you're trying to keep getting rid of lead you in the direction to which you need to go. So, sample problem. The Food and Drug Administration recommends that dietary sodium intake be no more than 2,400 milligrams per day. What is the mass in pounds if 1 pound equals 4.53, words are hard today, 453.6 grams. So I have a relationship between pounds and grams. I don't want grams in the end though. Note, in the end, I'm talking about milligrams. So now I'm going to have a second unit factor. I need to find a relationship between grams and milligrams, and they gave me the relationship between grams and pounds. Let's say, no, that's not bad. Let's say it was 1 meter equals 100 centimeters, but I was given cubic meters, and it was asking me about cubic centimeters, but I'm going to use this for my relationship. Then all I have to do is take everything to the third power. Okay. If it asked me for squared, I would raise everything to the second power. So whatever your base unit measurement is, you just bring all of that to the power it's asking you for. So if this is your base unit conversion, here it is. Okay. Exactly what I just wrote up here, the 1 meter to equals 100 centimeters. It's just the reverse. And to further explain very quickly, this top one here that I wrote, it's like saying 100 pennies equals $1. This one down here is like saying 1/100th of a dollar is equal to 1 penny. They still mean the same thing. It just looks and sounds a little bit different. So don't let that confuse you. Note, you have cubic centimeters here, but not cubic centimeters here. Well, then what I need to do is I can say cubic, because it's volume, 1 to the third cubic centimeters, 1 times 10 minus 2 cubed, meters cubed. Those are supposed to be 3s. This one section of my screen is not writing very well today, you guys. I'm sorry about that. So Here again is another sample problem, and it has to do with physical and chemical changes. I'm not sure why it's all the way here towards the end, but it is. So I want you to just go through the sample problem and see if you can figure